Okay, in this lecture, we will be covering logarithms. The way we define a logarithm is via the inverse function of an exponential. So remember we had covered our exponential functions, f of x equals a to the x, where a is greater than 0. We say the logarithm with base a of x is defined in the following way. Y equals log base a of x if and only if a to the y equals x for all x greater than 0. Recall, and let's look in this case where a is bigger than 1. So our exponential function y equals a to the x appears this way. And then we learned when we studied inverse functions that if we graph the line y equals x, we can reflect the graph about this line. So we see that the exponential has a y-intercept of 1, which means the log of base a will have an x-intercept of 1. And again, reflect it about the line y equals x. So this would be log base a of x. And because they are inverse functions, what this means is that they undo one another. So log base a of a to the x is x. Similarly, a to the log base a of x is also x. Now in this case, this works for x greater than 0. And then here, this would be any x. And you can note from the graph here, the domain of log base a are all the positive real numbers. And remember how the domain of a function syncs up with the range of its inverse. The range of this exponential is 0 to infinity, not including 0. And that means that's the domain of its inverse. The domain of the exponential is all the real numbers. Any x will work. So that means the range of log base a of x is all the real numbers. And this is basically the gist. This is the key property here, that they undo one another. Now, many of you have probably seen this sort of treatment of logarithms in high school. But what we want to do, figure out what these are, we can answer this by saying, okay, this is log base 10, which means it's the inverse function of 10 to the x. So what we want to do is try and write the argument here in terms of 10 to the x. Well, 1,000 can be written as 10 cubed. And now we use the fact that what we have here is log base 10 of 10 to a power, and the fact that log base 10 and this exponential of base 10 are inverses mean they undo one another, and we get that exponent, 3. Similarly here, we can write 0.1 as 10 to the minus 1. And the log base 10 and the exponential of base 10 undo one another, and we get an answer of minus 1. So again, this is just a special case of inverse functions. As long as the base of the log and the base of the exponent match, the functions will, in fact, undo one another. Now we have laws of logarithms, and you can see how some of these are derived in the textbook. The first one, log base a for any a of 1 is 0, and that's coming from the picture. So remember, the x-intercept of any logarithm is 1. And that's because of this reflection, because it's an inverse, the inverse of the exponential. So log of 1 is always going to be 0. A key property of logs is that it turns products into sums. So the log base a of x times y is the log of x base a. Log base a of x plus log base, this is a mistake, this should be a. Log base a of y. We can also write log base a of 1 over x as minus log base a of x. You don't really have to memorize this one because it's a special case. We'll jump to the fifth one. Log base a of x to the y, that power y can come out front, multiplying log base a of x. This third bullet is just the case when y equals minus 1, because here you can write log base a of 1 over x is log base a of x to the minus 1, and then we can use that property to bring the minus 1 out front. This property here. And it's a similar rule with this. The log base a of x over y is log base a of x minus log base a of y. So these are very useful rules of logs. And in fact, it's really because of this second and this fifth rule that logs are such handy functions. They come up in many different applications and in other uses in math, because these tend to be very handy properties in certain situations. Okay. Well, like good students of calculus, we have a continuous function. We made an argument that our y equals a to the x is a continuous function. So its inverse will also be continuous. Well, the exponential we also saw was differentiable, so its inverse will be as well. So what will that derivative be? And in order to do that, we need to use the following theorem. The function will allow us to calculate the derivative of a function's inverse. So let's think about the way the theorem is stated. We'll think about it graphically as we go. So this is telling us we have a differentiable function f defined on some open interval I, and f prime of x is positive for all x in that I, which means that any x, the tangent line has a positive slope, which means the function is increasing over that interval. That means that the graph of the function passes the horizontal line test over that interval, which means it can be inverted. So this first sentence sets up that there actually is an inverse. So we can conclude f has an inverse on that interval, and it's differentiable, and this is its derivative. So this is what we will use to calculate the derivative of log. So let's see this in an example first. Here we have inverse functions f of x equals x cubed and g of x equals the cube root of x. Now, if we were asked to find g prime of x, we know how to do this quickly. We know from our power rule, we bring that 1/3 out front, and then we reduce the power by 1. 1/3 minus 3/3 is minus 2/3. So we get from our power rule g prime of x right off the bat. But we can also use our theorem that g prime of x is 1 over f prime of g of x. And we can confirm that in this case, we get the same result as we would have if we just did power rule. Now, in this case, note that because f of x is x cubed, we know f prime of x from our power rule is 3x squared. So this g prime of x is 1 over our f prime, we just said was 3x squared. So we have 3 times. In this case, we're plugging in g of x. So 3 times g of x squared. G of x is x to the 1/3. And then you see when you multiply the exponents here, we get 1 over 3x to the 2/3, which matches what we have here if you wrote this with this x in the denominator. So in practice, you wouldn't calculate g prime of x this way if you were asked to do this question, but it illustrates that it actually does sync up with the answer that we would have gotten if we did it in the usual power rule sense. All right, now let's get into natural log. So natural log is the inverse function of the natural exponential. So remember, we had said the natural exponential was this function we called e to the x, where base e was about 2.71. It's an irrational number. The natural log, this is going to be basically the same picture we drew when we just drew a general log of base a. But in particular, this is a special case for a base. And we give it that special notation. We say log base e gets this special notation written ln of x for natural log. Its defining property, here we have inverse function of e to the x. So that means e to the natural log of x is x for all x in the domain of natural log, which is 0, infinity. And similarly, natural log of e to the x is x for all x in the domain of e to the x, which is the whole real line. Again, just a special case of a particular base for a log. But in particular, we have this. It's the inverse function of the natural exponential. Now remember, we had said the other day that if you take the derivative with respect to x of a to the x, that was a to the x times some expression that only depended on a. Well, it turns out that that m of a is actually natural log of a. So we can write that as a rule. The derivative with respect to x of a to the x is a to the x times natural log a. And you can see in the e to the x case, natural log of e, that's natural log of e to the 1. And the natural log and the exponential undo one another. So we can see that in the case where the base is e, we have e to the x times ln e, which is 1. So that ln a term drops out, only in the case when e is the base. But if you see something like, say, the derivative of 2 to the x with respect to x, you use that rule to say this is 2 to the x times natural log 2. Here, 2 is playing the role of a. So that's our natural log. And of course, we argued that e to the x was a continuous function earlier. And we actually saw that it was differentiable. So we should expect that its inverse is also differentiable. And that is true. And the derivative of the natural log of x is 1 over x. We can derive that using our previous theorem. So if we let f of x be e to the x, and its inverse g of x be natural log of x, then our theorem said that g prime of x, so the derivative we're after, derivative of natural log of x, is 1 over f prime of g of x. Well, if f of x is e to the x, its derivative is itself. So here, we can rewrite this as e to the g of x. When we feed g of x to f prime, that's plugging it in the power of e. G of x was natural log x, and because they're inverse functions, they undo one another. So we see, in fact, it is the case that the derivative of the natural log of x is 1 over x. How might we use this? Well, sometimes we're taking derivatives of functions that involve the natural log, like this case here. Now, let's use our chain rule, and let's be explicit first. Let's say f of x is, why don't we say g of u? So we'll have g of u is natural log of u. And u equals x cubed, so that we can actually write f of x in this way. So chain rule says f prime of x is the derivative of g with respect to u times du dx. The derivative of g of u with respect to u, well, that's our theorem we just proved. That's 1 over u. And du dx will be 3x squared. If we plug in for u, this is 3x squared over x cubed, or 3 over x. Now, you could have just skipped from seeing this f of x and writing f prime of x equals this, saying the derivative of the outer function, natural log, is 1 over whatever's inside. Leave the inside alone. That would give you the 1 over x cubed, times the derivative of the inside, which is the 3x squared. Either way is fine. I'm writing it this way so that it's clear how we're actually implementing chain rule. This is kind of like the long version of it. Alternatively, we could have used the properties of natural log, and note that this 3 could come out front. And that's going to be the quickest way, because then we see the derivative is just 3 times the derivative of ln x, 3 times 1 over x. Both ways are correct. This second way is a little quicker. Either is fine. Another example, here we use chain rule again. The derivative of the outer function, leaving the inner function alone. The outer function is natural log of something. So the derivative of the outer function is 1 over that something, times the derivative of the inside, which is 2x. So we'll want to be comfortable taking derivatives of functions that involve natural log like this. Another example, which comes up extensively in Calc 2, when you start doing integral calculus, is when we're dealing with natural log of absolute value of x. Now, the natural log of absolute value of x, its domain, you can give it anything but 0. So on the right, we have just natural log of x, but on the left, we have the mirror image. To do this, let's give that absolute value function a name, g of x. in which case then f of x is equal to natural log of g of x. Thus, f prime of x, using chain rule, will be derivative of the outer function, leaving the inner function alone, 1 over that inner function, times the derivative of the inside function. And again, g of x was the absolute value of x. So this is 1 over absolute value of x times g prime of x. And remember that the absolute value of x we had argued, so the absolute value of x is equal to x if x is greater than or equal to 0, and minus x if x is negative. So its derivative, if x was positive, the derivative was 1. If x is negative, the derivative was minus 1. So this was the derivative of the absolute value function. And it was not differentiable at 0. That means this is this function here. So this is going to be 1 over x. We have two cases. 1 over x times 1 if x is greater than 0, and negative 1 if x is less than 0. Think about what this says. This is telling us that in this case, when x is positive, the absolute value of x is just x. So we have 1 over x in that case. In this case, if x is negative, think like negative 3, the absolute value of x comes back with negative 3, or negative x. So we have 1 over minus x, but we have that minus 1. So this is just always 1 over x. And so this rule here that we're taking from this is that the derivative with respect to x of natural log of the absolute value of x is 1 over x. This will come up a lot in integral calculus. You'll use this extensively. But it comes from this analysis. So when you start studying integral calculus, and you start looking at integrating natural log terms, you may want to revisit this example. Okay, the last topic is one of logarithmic differentiation. Calculus textbooks write it as this procedure. This is not something to memorize. It's really understanding the method itself. So we have a three-step procedure to compute the derivative of a given positive function. What we do is you take y equals f of x, you take that expression, and you take the natural log of both sides. Once you do that, you differentiate both sides with respect to x. Then you solve for that derivative term. And this is usually something you use because you exploit the fact that the natural log of a times b is the natural log of a plus the natural log of b, or, and this is more common, the natural log of a to the b is b times the natural log of a. This can be handy because it turns products into sums, and it turns exponentiation into multiplication. This, again, being the most common situation, or the most common property of log that you're exploiting when you're doing this. So let's see how this works. When we look at this, we see a function, x to the x, that has the variable in the base and in the exponent. We have no rules to take the derivative of this directly. This is it's not an exponential because the base is variable, and it's not a polynomial because the exponent is variable. And what we do is use this idea of logs turning exponentiation into multiplication. So we first just write y equals x to the x, but now take the log of both sides. Our property of log allow us to take that x out front. So this becomes natural log of y is x times the natural log of x. Now this is something that we can differentiate. So in the steps we wrote before, this would be our first step. So our second step now, take derivatives of both sides with respect to x. So the derivative of natural log y is 1 over y, but y is a function of x, so we need dy dx. And so again, it's important to recognize that we're differentiating both sides with respect to x, and recognizing that this y is in fact a function of x. So we have this chain rule here. Now on the right, we do product rule. First times the derivative of the second plus the second times the derivative of the first. So this is 1 plus natural log of x. This is our second step. Now note, we're not finished because the goal is to solve for dy dx. So dy dx, multiply both sides by y times 1 plus natural log x. But of course, y was x to the x. So this is x to the x times the natural log 1 plus the natural log of x. And this was our third step. So again, the key is that, and this is the most common use of logarithmic differentiation, anytime you see an expression that has the independent variable in both the base and the exponent, logarithmic differentiation will help you and give you a way to actually do this. Again, we don't have a rule to do this derivative without doing this procedure. So this concludes the section on natural logs, but you'll want to be very comfortable dealing with natural logs. In particular, in a differential calculus course, we need to be comfortable taking derivatives of terms that involve log.